So this is the sixth lecture of work energy power. In this lecture, we have solved from question number 147 to question number 152. So these questions were mainly based on springs. Okay, so just see the lectures and denote the energy stored in a spring. How do we see the frame of reference? What are the conditions for maximum elongation and minimum elongation of a spring? Okay, so just follow through the lecture and just tell me if you like it or mention in the comment section. Okay, whatever doubts you have. Now in this question, there are two particles, okay, M1 and M2. Both these particles are moving in same direction. That means along x-axis. Okay, that means the motion is linear. Okay, one-dimensional motion. Fair and fine. Now the velocity of M1 is v1. The velocity of M2 is v2. Okay. Now what is the kinetic energy of the system? The kinetic energy of M1 plus kinetic energy of M2, or half M1 v1 square plus half M2 v2 square. But one thing you must realize is kinetic energy is dependent upon frame of reference. So because this v1 and this v2 are velocities of these two masses, and this v1 should be according to some observer, no? So in this question it is given that observer k, okay, out here whenever there is a frame of reference, no, we just assume a observer. Frame of reference means observer. Okay, the observer is seeing two bodies move in x-axis with velocity v1 and v2. Okay, the question is asking find the velocity of the observer. Okay, find the velocity of the observer from this frame of reference according to this observer. Find the velocity of observer in which the observer experiences or sees the minimum kinetic energy of the system. Okay, that means there must be some observer. Okay, there must be some observer k dash k1 dash. Okay, according to this observer, the velocity of this particle should be something like v2 minus velocity of observer. The velocity of this particle would be velocity v1 minus velocity of observer. So according to this observer, the total kinetic energy of these two systems should be minimum. Okay, understood? According to this observer k1, the total kinetic energy of these two particles is minimum. So the question is asking find the velocity of this observer. Find the velocity of this observer. Okay, so write down a note. Kinetic energy is minimum. Kinetic energy is minimum when the observer is at center of mass. When the observer is moving with the observer is moving with center of mass of the system of the system. Okay, that means when this observer moves with the same velocity as the velocity of center of mass of these two systems, then the kinetic energy as seen by this observer k1 would be minimum. Kinetic energy of the system as seen by this observer k1 would be minimum. So the first part of the question is find the velocity of observer k1. Velocity of observer k1 is nothing but velocity of center of mass or velocity of center of mass. Okay, and what is velocity of center of mass? Velocity, oh, velocity of center of mass is given by the formula m1 into v1 plus m2 v2 by m1 plus m2. Okay, so this is the answer to our first question. This is the answer to question number 1. Now the second part of the question is asking what is the kinetic energy of these two particles as seen by this observer. Okay, or what is the kinetic energy of the system as seen by this observer. So kinetic energy of the system as seen by observer k1. Okay, observer out here observer K1. Kinetic energy is equals to, or kinetic energy of the system, or kinetic energy of all the particles is equals to half mass of one particle, or mass of first particle, into velocity of first particle as seen by this observer. What is the velocity of first particle as seen by this observer? V1 minus Vcm, or velocity of one minus V center of mass square, plus half m2 into V2 minus Vcm square, or velocity of this mass as seen by this observer. Okay, now the remaining thing is algebra. Algebra means I'll substitute this velocity of center of mass out here and find out the kinetic energy as seen by this frame of reference. So kinetic energy of system is nothing but half m1 into v1 minus what is velocity of center of mass, m1 v1 plus m2 v2 divided by m1 plus m2, m1 plus m2 whole square plus half m2 into v2 minus m1 v1 plus m2 v2 divided by m1 plus m2 whole square. Okay, so out here if we see kinetic energy of system as seen by k1, or as seen by k1, is nothing but half m1. Okay, out here can I take m1 plus m2 as LCM? So m1 plus m2 as LCM, m1 plus m2. So if I take m1 plus m2 as LCM, I have to multiply v1 by this one. Okay, so m1 v1 plus m2 v1, I multiply this entire denominator. Okay, just wait a minute, I multiply this entire denominator with this v1 minus of m1 v1 plus m2 v2, sorry, not plus, minus, minus is outside, no, so it will be multiplied whole square. Now before solving this second part, let me just simplify this part. Okay, so m1 v1 and m1 v1 would get cancelled, this m1 v1 gets cancelled. Okay, so out here it would be m2 v1 minus m2 v2. Can I take m2 common? Of course. So this entire term would be m2 into v1 minus v2, m2 into v1 minus v2. Okay, whole square, whole square. Similarly, if I simplify the second term, it would be nothing but m1 into v2 minus v1. See, simplify the second term by m1 plus m2 whole square. Okay, now check one thing. Out here this is v1 minus v2, out here this is v2 minus v1. v2 minus v1 is nothing but negative of v1 minus v2, no? So if you multiply minus 1 into v1 minus v2, it would be v2 minus v1, and negative of square is same thing as positive of that square. So can I write v1 minus v2 whole square is same as v2 minus v1 whole square? So can I substitute this v2 minus v1, sorry, by v1 minus v2? This is the same thing, no? It doesn't make a difference, because as soon as you square a velocity, it becomes a scalar quantity. Okay, now what are the things that I can take common out here? See, half I can take common out here. I can take m1 plus m2 outside the bracket. Okay, out here this would get multiplied m1 m2. So if I take common things out here, okay, kinetic energy of system would be half m1 m2, okay, into v1 minus v2 whole square. Okay, I'm taking, see, I'm taking half. Okay, v1 minus v2, that's all. Let me take common, first common out here. I can take half common from both. Okay, or half, I can take m1 plus m2 square common from both, m1 plus m2 square. Okay, Out here I can take v1 minus v2 whole square common from both. v1 minus v2 whole square. The remaining terms are m1 into m2 square plus m2 m1 square. So m1 m2 square plus m2 m1 square. Okay, so if I resolve this, it would be kinetic energy of system as seen by k dash frame of reference is nothing but half v1 minus v2 whole square by m1 plus m2 whole square. Okay, out here, what can I take common? I can take m1 into m2 common out here, no? So if I take m1 into m2 common out here, what would I get? m1 m2, I would get m1 plus m2. Now this m1 plus m2 would get cancelled by this square. Okay, so our final answer would be this one. Okay, now I'm just reorganizing this answer. Our kinetic energy of the system is nothing but our kinetic energy of the system as seen by center of mass is half. Okay, I'm just reorganizing this answer out here. m1 m2 m1 m2 divided by m1 plus m2 into v1 minus v2 square. v1 minus v2 square. Okay, so remember this formula or remember this result out here. Whenever there are two particle system, the net kinetic energy as seen by the center of mass is nothing but half m1 m2 divided by m1 plus m2. This would be known as effective mass, and this one is nothing but relative velocities of one particle with respect to other. So remember this result, which is the answer to. Okay, this will come handy in question number 149. Okay, in question number 149 we'll use the same formula out here. Achha, in this question, okay, see what the question says out here. There are particles of mass m1, mass m2, mass m3. Okay, so there are many particles of these masses. Yeah, and they are kept inside a box for now. Achha, the question says something else. I am saying something else, but just at the end it will make some sense. Okay. Now, when I put a CCTV in this camera, okay, that means this CCTV is seeing this particle move with velocity v1, v2, and v3. v1, v2, and v3. Okay. What I'm doing out here is this v1, v2, and v3 velocities of this particle. These velocities are being observed by a CCTV out here. Understood? Okay. So the kinetic energy as observed by this frame is how much? Half m1 v1 square plus half m2 v2 square plus half m3 v3 square. Okay. Now see, this box is not accelerating. Okay. If this box is not accelerating, that means what? The center of masses of this particle are not accelerating. Okay. That means if you take this entire thing as a system, the net force or the net external force on this system is equals to 0. You have to remember these things. And what is the kinetic energy as seen by this camera? Kinetic energy as seen by, let's say, this camera as center of mass. Okay, why I'll tell you a little bit later. Half mv1 square plus half mv2 square plus half mv3 square. Okay, and this kinetic energy is given as E. This kinetic energy is given as E dash in the question. Okay, E dash. This one. E dash. Fair and fine. Okay. Now there is another frame of reference out here. There is another observer out here. And let's say this observer is K. Okay. Now what happens? Now after a certain while, the box moves with velocity v. That means it accelerated and moved with velocity v. That means after it started moving with velocity v, okay, it already started moving with velocity v. the acceleration is neglected, all the things from 0 to v is neglected. Okay, all I'm saying is this box, this observer is seeing this box move with velocity v. Fair and fine. Okay, or say some observer was out here who accelerated backwards with velocity v, and he is seeing this box move with velocity v. That's the main point I'm making out here. Do not get confused between the acceleration of this block or acceleration of this particle. Let's say observer out here moved with velocity v in backward direction. Okay, is moving with velocity v in backward direction. So what will you see this box move with? He'll see this box move with v in forward direction, isn't it? Now the question is saying, what is the total kinetic energy of the system? Okay, as observed by this observer. So the total kinetic energy as observed by frame of reference K, or as observed by observer K, the total energy E, the total energy E as observed by K is nothing but half m1 into velocity v1 as observed by this frame. Okay, so what is the velocity v1 as, what is the velocity of m1 as observed by this frame? This velocity plus the velocity of m1, or v plus v1. Okay, see, you can either give velocity to the box, or you can take velocity to the observer in opposite direction. Both will have the same result. So half v plus v1 square plus half m2 v plus v2 square plus half m3 v plus v3 square, and so on. If there are 4 masses, then half m4 v4 and so on. Okay, now see, one thing you must note out here or observe out here. There is no external force acting on the system. Observe out here. Okay, observe. No external force is acting on the system. No external force is acting on the system. Is acting on the system. Therefore, the net change in momentum or total change in momentum of the system is equals to 0. Therefore, change in momentum of the system or total change in momentum of all the particles, okay, or net change in momentum of all the particles mi vi means nothing but m1 into v1 plus m2 into v2 plus m3 into v3. That is the net momentum of the particle. Okay, the total change in momentum of this particle would be equals to 0. Okay, or net momentum of the particle as seen by this observer is equals to 0. Okay, that means what have I written out here is, if any observer sees out here from this camera, okay, he'll see that net momentum of all these particles inside the box is equals to 0, because the box is not accelerating anywhere. No, understood? Okay, that means from this observer the total change in momentum or total momentum of all the particles, not change in momentum, total momentum of all the particles is equals to 0 from the observer inside CCTV. So half m1 v1 plus m2 v2 plus m3 v3 is equals to 0, and this v1 v2 and v3 are seen by this observer. Okay, for an outside observer, that is either moving with velocity v in backward direction, or I can move the velocity of box in forward direction v. Okay, the kinetic energy as observed by this observer is this value, and let me elongate this value. E is equals to half, okay, m1 into v plus v1. V plus v1 is nothing but a plus b whole square, or v square plus v1 square plus 2v v1 plus half m2 v square plus v2 square plus 2v v2, and so on, isn't it? Now see, now can I multiply this half m1 into v square plus half m1 into v1 square plus half m2 into v2 square? So if I do something like that, it will become, see, E is equals to half, I'm just multiplying m1 v square plus half m1 v1 square plus half into 2v v1, sorry, m into 2v v1, m1 into 2v v1, similarly plus half m2 v square plus half m2 v2 square, okay, plus half, okay, m2 into 2v v2. So can you look at the pattern out here? See, this will keep repeating. See, if there are three masses, okay, there will be half m1 v1 square, half m1 v1 square plus half m2 v2 square, okay. So if I rearrange these values, okay, energy of the system can be written as seen by this observer, can be written as energy as seen by K is equals to half m1 v1 square, okay, I'm taking this value, plus half m2 v2 square plus half m2 v2 square. If there was any third particle v3, plus half m3 v3 square plus half m3 v3 square, okay, and so on, okay. Now let me take these values, let me observe for this kind of values. Acha. First one is this kind of values, this is the first kind of values. Now see this one, okay, this type of values, half m1 v square plus half m2 v square plus half m3 v square. So this plus half m1 v square plus half m2 v square plus half m3 v square, okay, v square plus half m4 v square and so on, okay, if there are four particles. Now let me take the third kind of value, okay, this one, half m1 into 2v v1, okay, half m2 into 2v v1, so out here plus half m1 into 2v v1. Acha, let me simplify this 2 and this 2 will cut, no, so it will be m1 v v1, so it will be m1 v v1, m1 v v1 plus m2 v v2 plus m3 v v3 and so on. Understood? So the total kinetic energy of all the particles as seen by this frame is nothing but these values. Okay, I just rearrange this entire equation in this format. Okay, now see, if I see these values, okay, if I look at these values out here, if I look at these values out here, what are all these values? The additions of all these values are nothing but this energy, see, or a kinetic energy as seen by center of mass. Okay, so this is nothing but E dash or kinetic energy as seen by the CCTV. Okay, so this is nothing but E dash. Okay, now can I say, see out here, if I take all this summation, half m1 v square plus half m2 v square, so can I take half v square common? So this is nothing but half into total mass. See, if I take out here, if I take out here, these values is nothing but if I take half v square common, half v square common, it would be m1 plus m2 plus m3 and so on, okay, and m1 plus m2 plus m3 is nothing but the total mass of the system, see, equals to the mass of the system of particles is equals to m. So m1 plus m2 plus m3 is equals to m, which is equals to m. This is nothing but m. Okay, now the third part, if I take v common out here, okay, for the third part, if I take v common out here, it would be m1 v1 plus m2 v2 plus m3 v3. Now what is m1 v1? Product of mass into velocity is what? Product of mass into velocity is momentum, isn't it? So momentum, and who is this velocity v1 seen by? The v1 is velocity as seen by the CCTV. Okay, so check what I'm writing out here. If I take this entire third part, okay, sorry, a little bit. Let me take this entire third part. If I take v common, if I take v common, it would be m1 v1 plus m2 v2 and so on. Okay, what is m1 v1 plus m2 v2 plus m3 v3? It is nothing but the momentum of the system. m1 v1 product of mass into velocity is nothing but the momentum, no? So m1 v1 is nothing but momentum of the system as seen by this CCTV. m2 v2 is nothing but the momentum of the system as seen by this CCTV. Okay, and what is the net momentum of this system as seen by this CCTV? Zero. Why? Because no external force is acting on it, and this box as seen by this CCTV is static, no? This box, okay, as seen by this CCTV is not moving anywhere. Okay, so if the system is not moving anywhere, what will happen? The velocity of center of mass is equals to 0, and if the velocity of center of mass is equals to 0, the net momentum of the system is equals to 0. You're getting what I'm trying to say? This velocity or this box, okay, as seen by this frame of reference, is not moving anywhere. Okay, so the total momentum of the system or the velocity of center of mass as seen by this camera is equals to 0. So if the velocity of center of mass as seen by this camera is equals to 0, that means what? The total momentum of the system is equals to 0. So can I say m1 v1 plus m2 v2 plus m3 v3 plus m4 v4, or total momentum of the system as seen by this CCTV is equals to 0. So total momentum of the system is equals to 0. So what we get in our answer is kinetic energy as seen by this frame of reference is equals to kinetic energy as seen by this frame of reference plus half total mass into velocity of the frame or velocity of the frame square. Understood? Kinetic energy as seen by, see, I'll write the answer. Kinetic energy as seen by this frame of reference is equals to kinetic energy as seen by this CCTV, which is given as E dash, plus these values is nothing but half into v square into total mass, so half m into, so plus half m into velocity of frame square, or half into v square. So this is our answer. Okay, now I'll get to the confusion. See, I made a box out here. In the question, instead of giving a box, they have named it a frame of reference something, or frame of reference of center of mass. Okay, this is the frame of reference of center of mass. Understood? Instead of making a box, I just made the box so it is easier to understand for you. Okay, so this is question number 148. So in this question, okay, there are two particles, m1 connected by a spring to m2. They have velocities which are mutually perpendicular. v2 is in this direction, v1 is in this direction. That means velocity of 2 is perpendicular to velocity of 1. And who are these velocities being observed by? These velocities are being observed by someone on the ground. Okay, now the question is asking, find out the velocity of frame of reference from center of mass. So find out the kinetic energy as seen by someone sitting in the center of mass of the system. Okay, one thing, see, this question, this exact kind of question I have done in question number 147. Look up the previous video. Okay, question number 147 has exactly the same question, where kinetic energy as seen by center of mass. See, this center of mass will move with certain velocity. Okay, VCM. So the kinetic energy as seen by center of mass is equals to half equivalent mass. Equivalent mass was equals to m1 m2 by m1 plus m2. See the formula in question number 147. I told you to memorize it. Okay, into relative velocity of one with respect to relative velocity of other square. You can either take frame 1 and take the relative velocity of frame 2 with respect to frame 1, or you can either take frame 2 and take the relative velocity of frame 2 with respect to frame 1. Okay, both will be same thing because I'm squaring out the velocity. Now see, what is the relative velocity of v1 with respect to v2? See, v2 minus v1, or v2 minus of v1 is nothing but in this direction. Okay, so relative velocity or v2 minus v1 would be this vector, and this vector is nothing but under root of v2 square plus v1 square. Okay, is equals to magnitude of v2 vector or v1 vector minus v2 vector. See, sorry, v2 vector minus v1 vector, magnitude of v1 vector minus, sorry, v2 vector minus v1 vector, minus v1 vector because I have reversed the direction of minus v1. No? So can I substitute this parameter out here? Do not get confused between v1 minus v2 and v2 minus v1. Since I'm squaring it, the negative will already get disappeared. I can write the same parameter as v2 minus v1. It doesn't make a difference out here. v2 vector minus v1 vector, v2 vector minus v1 vector, because square of velocity is a scalar unit. Okay, whereas velocity itself is a vector unit. Whenever you square any vector quantity, it becomes a scalar quantity. Okay, and out here, so what is the magnitude of v2 minus v1? Under root of v2 square plus v1 square. So kinetic energy of the center of mass is equals to half into equivalent mass m1 m2 divided by m1 plus m2 into v2 square plus v1 square under root, and under root of this square would be nothing but this parameter. Okay, what I'm going to discuss out here is more important. Okay, I'm going to discuss out here, will the kinetic energy, see, this spring can cause the change in velocity of this one. No? Okay, the spring when compressed or elongated can cause the fluctuation of velocities of these two parameters or these two velocities. So why am I not taking the accounting factor of spring? See, spring will be internal force. Internal force means if I apply conservation of energy, that means change in kinetic, sorry, work energy theorem. Okay, conservation energy and work energy theorem are more or less the same thing. Okay, conservation energy of energy you can only apply in conservative forces, whereas work energy theorem you can apply it everywhere. So in your entire chapter, instead of using conservation of energy and this and that, just simply apply work energy theorem. Okay, it's much simpler, it can be applied everywhere. You just have to learn the nuances of work energy theorem. Okay, so if I apply work energy theorem out here, okay, if I apply work energy theorem out here, simply say that change in kinetic energy of this body would be work done by all the forces. So if the spring force is doing some work out here, if it is suppose the spring is compressing, okay, out here the negative work done by the spring would be equals to the positive work done by the spring in this body. Understood? I have to apply work energy theorem in these two bodies, no, because the spring out here is massless. So the negative work done on this body by the spring would be equals to positive work done by the spring on this body. Okay, understood? See, if it is kx out here in this direction, it will be kx out here in this direction. Okay, kx into this velocity in this direction, kx in this direction into velocity in this direction. So out here you can say that spring is an internal force. Internal force means work done by spring on this body would be equals to work done by spring on this body, negative of work done by spring on this body. Understood? In this question, okay, there are two masses m1 and m2. Now they are connected by a weightless spring. That means the mass of this spring is equals to 0. Okay. The velocity of them are v2 and v1. The direction of v2 and v1 are not specified in the question. Okay. The question is saying neglecting air drag or air friction, Find the time dependence of the total momentum of this system process of motion and the radius vector of its center of inertia relative to the inertial position of the center. That means find out the momentum as a function of time. In which direction is the acceleration due to gravity acting? Downward. Okay, so can I say center of mass or velocity of center of mass is equals to how much? m1 v1 plus m2 v2 divided by m1 plus m2. Okay, and what does this center of mass represents? This center of mass represents that this m1 and this m2 plus this spring is considered as a whole system, and this whole system is moving with a velocity that is equals to this velocity of center of mass. Okay, and this whole system is being acted by acceleration due to gravity. Okay, so what will be the velocity after some time? This is the initial velocity, no? v2 and v1 are the initial velocity. So this center of mass, velocity of center of mass would be the initial velocity of center of mass. Okay, suppose I need to find out the final velocity. Which formula do I use? V is equals to u plus at. And why can I use this? Because acceleration is constant. Okay, v is equals to u plus at. V is equals to u plus at. Okay, now in projectile motion, mostly in cases of projectile motion, what did you do? You separated the velocity in x component and y component, no? And then solved the equation and then solved the problem. Okay, but the fundamental formulas you applied are these formulas only. What if I say you can apply the formula directly? That means v vector is equals to u vector plus a vector into time vector. What I mean by that is, first let me solve the problem, then I'll tell you what I'm trying to explain corresponding to projectile motion. Okay, v vector is equals to u vector plus a vector. So velocity at some final time v is equals to u. What is u? U is nothing but this velocity of center of mass, m1 v1 plus m2 v2 by m1 plus m2. Okay, plus acceleration. What is the value of acceleration? G vector downward. Okay, so plus g into t. And what does this v give us? This v gives us the velocity of center of mass at this time. Okay, assuming that velocity of center of mass at time t is equals to 0 is this value. Fair and fine. So what is the momentum at this time t? Velocity at time t. Let me write down now. Velocity at time t. Okay. Similarly, what would be the momentum at time t? Momentum at time t. At time t would be mass into velocity. What is the formula for momentum? Momentum is nothing but mass into velocity, no? So what is the total mass of the system? m1 plus m2. m1 plus m2. And what is the total velocity of the system? Total velocity of the system is nothing but the velocity of center of mass of the system. Okay, so into velocity of center of mass of system at time t, m1 plus m2. This is our final answer. This m1 plus m2 and this m1 plus m2 would get cancelled. Okay, so net momentum or total momentum at time t would be equals to m1 v1 plus m2 v2 vector. Plus gt. I forgot a parameter to add out here. This parameter I forgot to add out here. See, I made a mistake in equation. So plus gt out here. So it won't get cancelled. Sorry, do not cancel it. Plus gt out here. Plus g into t. Okay. Now let me multiply this m1 plus m2 by both this factor. Okay, so final momentum would be, or momentum at time t is equals to m1 v1 plus m2 v2. Acha, there are vectors out here, plus m1 plus m2 into g vector into t. Okay, out here these are vector quantities, vector. Now what do I mean by, I was talking something about projectile, no? So what do I mean by E means these formulas are vector quantities? See, in projectile motion, okay, just to apply three formulas, AC is equals to ut plus half at square, v is equals to u plus at, okay, and v square is equals to u square plus 2s. Apart from the third formula, okay, the first two formulas, AC is equals to ut plus half at square and v is equals to u plus at, the first two formulas are vector formula. Vector formula means, see, whenever you apply v is equals to u plus at, is to divide them into vectors, x component of v is equals to u plus at, y component of v is equals to u plus at. What used to happen is that, see, in projectile motion, okay, suppose v theta, okay, so is to apply v horizontal component v cos theta, vertical component v sin theta, then is to apply AC is equals to u plus at, AC is equals to ut plus half at square. You can write this same formula, as vector, okay, is equals to u vector is nothing but, see out here, let this be u cos theta I plus u sin theta j, okay, into t plus half g is nothing but minus gj. G used to be in downward direction, no? So g only has j component, so minus g j, okay, into t, what I did out here is, see, this formula s is equals to ut plus half at square gives both the x component and y component. See, because this I will only interact with I and j will only interact with j, and that is why in projectile motion you can divide the components into x component and y component, because in vectors I only reacts with I and j only reacts with j in addition, subtraction and dot multiplication. Understood? So it's the same thing as these two first formulas are the vectors formulas. That means you can write it in this format, or this can be written as u vector. This entire thing, okay, can be written as u vector, and this entire thing can be written as g vector. This entire thing can be written as g vector. This was the original formula. Okay, to simplify things, we made it into x component and y component. Similarly, when you get the s vector, you would get the x component of x vector and y component of x vector in the same form. Understood? So this is the point I was making out here. Okay. And the second thing, there's a second question I have out here. This is a spring, no? So when this spring be getting compressed or elongated, and when that compression or elongation change this velocity, obviously they will change the velocity. But if you observe closely, okay, this spring is an internal force. Internal force means positive work done by the spring on this body would be equals to negative work done by the spring on this body. Okay, so this positive work and this negative work would get cancelled, so total work done by the spring in this two body system would always be equals to 0, and that is why spring is an internal force. That is why you do not take into account of the spring. Okay, the variation of this question can be, see, find the maximum or minimum elongation of the spring. Okay, there is a variation of this problem, find the maximum or minimum elongation of the spring, and that will solve in following problems of following upcoming questions. Okay, that type of questions are there. In this question there are two blocks. Okay, block of mass m1 and m2. Okay, now this m1 and m2 are connected by a weightless spring. the spring constant is given by x out here, but instead of x we'll use k. So it is much more familiar. Okay. Okay. Stiffness is nothing but spring constant that is given out. Okay, then fine. Now this M2 is being compressed by distance x. Okay, this M2 is being compressed by distance x. That means this M2 is being pushed by distance x. Okay, so when it is being pushed by distance x, the new position of the block M2 would be this one, and it would be connected by the same spring or same spring constant. Okay, now the question is asking, when the mass M2 is released from this point, what will happen? This mass M2 will go forward, and after a certain while what will happen? These two masses are joined, no? So as soon as this mass M2 moves towards a certain length, it will have some velocity and it will pull the spring, no? If it pulls the spring will pull back the M1. Okay, the question is asking, find out the velocity of M2 at the moment M1 gets detached from this wall. Okay, find out the velocity of M2, no sorry, find out the velocity of center of mass of the system, not M2. The question is asking, find out the velocity of center of mass of the system. That means center of mass of M1 and M2 when M1 detaches from the wall. Okay, and when does M1 detach from the wall? The moment spring force becomes anything, the moment spring force becomes in this direction of any value, 0.00001 amount of spring force in this direction will also cause this M1 to detach from the wall. Why? Because this surface is frictionless. So as soon as the spring force becomes elongative, okay, or the spring force on M1 becomes towards right hand direction, what will happen? M1 will detach from the block. Okay, so what do you have to do? You have to find out the moment, okay, this M after being compressed by distance x, okay, reaches back to this position. Understood? So I have to take this position A, this as position A, and at this position B, when the spring return back to its normal length, what will happen? M1 will get detached. Why? Because after returning back to its normal length, it will go towards right, no, with some velocity. And as it goes towards right with some velocity, it will stress the spring. And as the spring is stressed, the spring force would be towards right, and M1 would get detached. Okay. So applying work energy theorem, from A to B, from A to B. Okay, what is the velocity at A? After I stressed it, I kept it at hold, no? So velocity at A is equals to 0. And when it elongated, let the velocity at M2 be V. So when it reached back the position B, let the velocity of block M2 be V. Okay, so I'm applying work energy theorem only on block M2. On block M2. Why, you'll understand in a moment. Okay, because if you apply work energy theorem on the entire system, no, the equation will get confusing. Okay, so let's analyze this block. Initial kinetic energy is equals to 0. Final kinetic energy is equals to half mv square. So final kinetic energy half mv square minus initial kinetic energy, which is equals to 0, is equals to work done by all the forces. And what is the only force doing some work out here? The only force that is doing some work out here is the spring force. So is equals to half k x square, but x is the elongation to its natural length. Now it is minus half kx square or plus half kx square. It is plus half kx square. Why? Because spring force is in right hand direction. Observe only on block M2. Spring force is on right hand direction and the displacement of M2 is also on right hand direction. So it would be positive work. So half kx square. So if you solve this equation, okay, half and half will get cancelled. So mv square is equals to kx square, or mv square is equals to kx square. I can take the m out here. Okay, and if I square root it, it would be v. So v is equals to under root kx square by m. So the velocity of block 2 when it reached out here, okay, is what? How much? Kx square by m, m2, because I'm analyzing only block 2, m2. Now the question is not asking the velocity of block 2. The question is asking the velocity of center of mass. Asha. So as soon as it reached out here, okay, the block m1 would start accelerating towards right. What is the velocity of block 1 as soon as it left the wall? It is very less, no? The velocity is 0.000 something. It is just starting to move. So velocity is nearly equals to 0 when the block left the wall. Okay. So I have to find out the velocity of center of mass. Velocity of center of mass, therefore velocity of center of mass is equals to mass 1 into velocity of 1 when it detaches from the wall, plus mass 2 into what is the velocity of 2. Velocity of 2 when it detaches from the wall is nothing but kx square by m2. So under root of kx square by m2 divided by m1 plus m2, m1 plus m2. Okay, so the velocity of center of mass, see, in irodov center of inertia and center of mass are the same, okay, is equals to nothing but m2 by kx square by m2 divided by m1 plus m2. Now as the answer is given, the answer in the answer x is, okay, and this m2 is divided and made under root, okay, it would be something like this. It would be, see, x I can take it outside. This m2 can be written as root over m2 into root over m2. So if I cancel out this one, it would be something like this. So x under root of km2 divided by m1 plus m2. This is the answer. Okay. To solve this kind of question, you need to remember a general statement. Okay. Anytime the body is acting under a conservative force, okay, the body acting under the influence of a conservative force at extreme positions. Extreme position means what is the maximum height in gravitational force or in a projectile motion, or what is the maximum elongation of the spring. At extreme position, the velocity of the body is equals to 0. Okay, any body acting under the influence of conservative forces at extreme positions, the velocity of the body is equals to 0. Okay, so just remember this general statement. Understood? Now to understand this question, you need to first understand a certain concept out here. Okay, so imagine a scenario. Okay, this is nothing related to this question. Imagine a scenario, a spring. Okay, a block of mass m is hanging by the spring. Okay, so out here, when the block is just hanging, okay, can I say mg or gravity force is equals to spring force? Okay, now what did I do? I compress the spring by distance x. I compress the distance by x. Okay, this much distance is x. This much distance is x. Okay, I pulled up the mass m by distance x. Okay, what will happen as soon as I leave it? The mass m will come down, but will it stop out here? No, the mass m will come down out here. It will have certain velocity out here. Okay, because spring force is doing some work, and after that it will go. It will extend up to certain time, and then again come back, then again go up, then again come down, again come up till this much distance, again go up. So it will start vibrating, no? So it will start oscillating. Okay, the distance with which it will oscillate is x. How and why, that will be explained in later part of the chapter called SHM. But right now, if I pull up distance x, what will happen? Okay, it will come down to its normal position where mg is equals to kx, and then again it will add some or extend up to some additional distance of x. What is the velocity out here? The velocity of block M out here is equals to 0. The velocity of block M out here is equals to 0. So when the block is at topmost position, the velocity would be 0. Then again it would come down. Out here velocity would be maximum. Again it would come down and velocity would be 0 out here. Then again it would go up. So it would start oscillating. Now the same setup. Okay, I'm drawing in horizontal position. But instead of a constant force of gravity acting downward, I'll give a constant force of F towards right. Okay, what will happen? The same thing will happen. Okay, suppose this mass is compressed by distance x. What will happen? It will start oscillating, and the amplitude of oscillation or the total distance of oscillation is how much? 2x. Is that understood? Okay. Now at the extreme end, okay, what is the velocity? Velocity is equals to 0. At the extreme end, that means when the spring is fully compressed or when the spring is fully elongated, the velocity of body is equals to 0. Okay, but now you might ask her, you are attaching the spring to a fixed body, but out here this body m1 can move, m2 can move. How can you solve this from this question? Okay, how is this question related to this question? Just wait for a minute. If I shift my frame of reference to the center of mass, okay, that means if my observer is sitting at center of mass, now see what will happen. This force is collectively moving this system m1 and m2. Okay, the acceleration of center of mass will depend upon this force. Will the spring force cause any acceleration of center of mass? No. Why? Spring force is an internal force. Understood? So spring force will not participate in the acceleration of center of mass. Now see, is this problem, if I shift my observer from the ground frame of reference to the frame of reference of center of mass, or if I shift my observer from ground to the center of mass, does this problem become same as this problem? Obviously. Okay, at maximum elongation, okay, at maximum elongation of the spring, the velocity of m2 with respect to center of mass is equals to 0. At minimum elongation of the spring, okay, or at maximum compression of the spring, the velocity of m2 with respect to center of mass, that means velocity of m2 observed from center of mass is equals to 0. Okay, so the necessary condition out here is velocity of m2 would be 0 as observed from center of mass. Understood? So let me erase this one. So write down a note. Okay, for maximum and minimum elongation, velocities of the bodies are equals to 0. For maximum and minimum elongation, for max and minimum elongation, velocities of the body, velocity of the body is equals to 0. Now this velocity is observed from center of mass. Why? Because both the masses are moving. If you observe from this frame of reference, okay, both the masses are moving, no? So you won't get a proper calculation. Understood? So in order to form a proper calculation, you must shift your observer to frame of reference of center of mass, or you must shift your observer to center of mass. Okay, so according to center of mass, m2 will go outside, okay, then stop at maximum elongation, again come back and stop at maximum elongation. So it will oscillate with maximum elongation and maximum compression from the frame of reference of center of mass. So in order to find out the acceleration of center of mass, can I write total force acting on the system or total force acting on m1 and m2 is equals to mass into acceleration, mass of the system into acceleration of center of mass. Okay, now will this acceleration of center of mass be affected by the spring force? No. Why? Because spring force is an internal force. Understood? Okay, So the acceleration of center of mass is equals to F by m1 plus m2. This much is understood. Fair and fine. Now this center of mass, okay, has an acceleration of F by m1 plus m2. So acceleration of center of mass is equals to F by m1 plus m2. Okay, F by m1 plus m2, and this is nothing but the center of mass. This much is understood. Okay, now as observed from the center of mass, okay, this center of mass is an non-inertial frame, that means an accelerating frame. So m2 and m1 will be an pseudo force, will observe an pseudo force. Okay, you can analyze any block. You can either analyze block m1 or you can analyze block m2. Both will have the same effect. Okay, so I'm analyzing block m2. So apply work energy theorem on m2. Applying work energy theorem on now if you look at block m2, what is happening to block m2? It will gets elongated by distance x. Okay, and out here the velocity of m2 will be 0 at maximum elongation. Okay, at maximum elongation of the spring, the velocity of m2 is equals to 0. The initial velocity is equals to 0. Remember, these velocities are being observed by an observer sitting on the center of mass. Okay, understood? So initial velocity of m2 is equals to 0 at maximum elongation. After elongating a distance x, the velocity becomes 0. So can I say change in kinetic energy? What is the final kinetic energy? 0. What is the initial kinetic energy? 0. These kinetic energies are also from observers sitting in the center of mass. So final kinetic energy minus initial kinetic energy, 0 minus 0, is equals to work done by all the forces. What are the forces acting on it? The first force is external force. The second force is spring force. There is one more force acting on this block M2. Can you guess which one is it? It is nothing but pseudo force. Why? Because this observer is also accelerating, no? So this observer is non-inertial. So non-inertial observer causes a pseudo force. Okay, so this M2 will also experience a pseudo force. So the work done by external force is nothing but F into X. Work done by spring force is nothing but minus half kx square. Why minus? Because spring force is in opposite direction. If I stress the spring force will act in this direction, whereas elongation is being in this direction. And what is the work done by pseudo force? First of all, what is pseudo force? Pseudo force is nothing but m2 or mass of m2 into acceleration of observer in opposite direction. So pseudo force is nothing but minus pseudo force. What is pseudo force? Mass of m2 into acceleration of observer in opposite direction. This is the pseudo force, and the work done by pseudo force is negative. Why? Pseudo force is acting on this direction, displacement is happening in this direction into x. Where this entire thing was force, this thing is displacement. Now what you have to do? You have to solve for the value of x. Now see, if I take x common, x square and x will get cut. Okay, so if I rewrite this equation, 0 is equals to f minus half kx minus m2 f by m1 plus m2. Okay, what do I need to solve for? I need to solve for x. So if I bring half kx is equals to f, if I take f common, 1 minus m2 by m1 plus m2. Okay, if I take m1 plus m2 as LCM, this entire thing would be m1 by m1 plus m2. m1 by m1 plus m2. Okay, just take the LCM and tell me. These two will go to the right hand side to become 2, and this k, these two already went to the right hand side, and this k would come downward, so it would be k out here. So the maximum elongation of the spring is equals to 2 into F into m1 divided by k into m1 plus m2. Okay, now see, this is the second part of the question. Okay, if m1 and m2 are different, what happens if m1 and m2 are same? Same equation, except for the fact m1 is equals to m2. So let's say first part of the equation, x is equals to 2fm, where mass is equals to same for both, by k plus m1 plus m2, where m1 is equals to m and m2 is equals to m, is equals to 2m. Mn gets cancelled, 2 gets cancelled, is equals to f by k. Okay, so this is our answer to the first part.